lecture we will continue from that point. So we'll continue with mechanical waves from that point onwards. Meanwhile, some of you had some doubts, we can discuss those also. So in fact, I will start with some of the doubts that have been sent to me. And we'll take it from that point. So I'm starting with a couple of doubts that have been sent to me by some of you. So there is this, okay, Dantresh, I'll come to that also. This you're saying from the SHM chapter or? Yes, very good. So we'll discuss that next. Okay. Diti, I'm discussing a couple of the doubts that you have sent, even though they are from the previous chapter, but do a quick revision of those concepts through that. So this is one of the questions. We have a situation like this. If I'm not mistaken, this is a question from the module. So this whole situation is inside a fluid. So we have a hollow sphere of mass m, radius r, which is immersed in water which has density rho w. Okay. The sphere is tied at the bottom by two wires. So these two are two threads or wires which are like this at 45 degrees. So the tension in the wires we have to calculate. So we want to find the tension in the wires. So basically the method to do this, Diti, is make the free body diagram of the sphere. Okay. Forces on it will be weight, okay, buoyancy or buoyant force, and tensions. Okay. So balance the forces for equilibrium, and you should get the value of the tensions. Okay. So in case any of you have not tried this question before, it is from your module from the fluid mechanics section. Just try it out. So just follow the instructions which I'm given here. I'll put up the free body diagram in a moment. Okay. So this is the first question we'll do. Then we are also doing HC Verma SHM questions. So if you have HC Verma with you right now, you can start going through these questions. We'll discuss them very shortly after doing a couple of more doubts from earlier chapters. So these are the questions from SHM which we'll be discussing. Okay, so looking at the free body diagram, there is buoyant force acting because of water. So that buoyant force will be equal to what? It will be density of water into volume of the cube into G. Okay. And there will be weight of the block. Okay. Now it is understood that buoyancy is greater than weight, because it is given in the question that the sphere would float if not tied by the wires. So it was not tied to the bottom, it would have floated. That's what is telling me that buoyancy is greater than mg. Okay. And therefore, if this tension is, let's say, T1 here, this tension is T2. So from symmetry, you'll see T1 and T2 are equal because they're acting at symmetrical angles. So the equilibrium condition now is that and buoyancy has to be the sum of and theta is equal to 45 degrees. So solving these two equations, you can quite easily see that we'll have the relation that 4 by 3 pi r cube into density of water into G is equal to 2T into 1 by root 2 plus mg, where T1 is equal to T2 is equal to T. So this should give you the answer. Hope the question is clear, Diti. Okay, very good. So make a note of this if required. Let's come to the next question. So the next question also is to do with the concept of buoyant force. So it says that we have a combination of two cylinders which are of same cross section and length. Okay, so we have, let's say, two cylinders which are made of different materials but having the same cross sectional area and the same length. Okay. Now this is made of material of density D1 and this is made of material of density D2, and the combination floats, seems the combination floats in a liquid of density D with a length L by 2 above the surface of the liquid. So the combination floats like this in a liquid of density D such that this length above the liquid is L by 2, this part of the length. Okay. So if D1 is greater than D2, then find the relation between D1, D2 and D. Basically, that's what we have to do. From that, we have to match the options. Okay, Krish, I will take you back to the earlier question solution also. Okay, so same principle you have to apply in the second problem also, Diti. Buoyant force, will make a FBD of the combined object and show the forces acting on it. Only in this case, there are only two forces, the weight and the buoyant force. Okay, the weight you can write as the combined weight of the two objects, okay, and the buoyant force is according to the formula of Archimedes principle, balance, and you'll get the relationship. Okay, so hope you've tried with the free body diagram method here. So on this combined object, both the cylinders together and all that, what will be the buoyant force that will act? The buoyant force will be density of the fluid into volume of the submerged part into G. That's the general formula. So let's say the cross-sectional area is, let's say, E. Okay. So the submerged part has a total length of how much? L plus L by 2 or 3L by 2 and an area is. So this will become D into area into 3L by 2 into G, right? And then the weight is basically M1 plus M2G, which is this. And this is keeping it in equilibrium. So ultimately what we see by balancing the forces, that the weight is balanced by buoyant force, we see that D into 3L by 2 will come out to be D1 into L plus D2 into L. In fact, L is also cancelled out. On implementing this equation, we'll see that 3 by 2D is equal to D1 plus D2. Now you can see that if D1 is the larger one, let's say D1 is equal to D2 plus X. Okay, so you can substitute that over here like this. Okay, very good, Diti. So this is also pretty straightforward. Okay. Okay, next question. So this is a situation like this, that we have, the question tells us that there is a large container with liquid in it, such that a cubical block is floating. So this cubical block, okay, of side length A and mass M floats with 4/5 of the volume submerged. That is the first information that is given. Okay. Now from here, what is happening is that on top of that block, we are placing another mass, so such that it is just about completely submerged. So on top of this block of this dimension, this mass, now we are placing another object. Say we are placing an object of mass small m. So find small m such that the block floats with almost the full volume submerged. Yeah. So again, make FBD in each case. Make the FBD for this, then make the FBD for this. You'll get the relation. Okay, Dhandresh, I'll look at that question also. Okay, let's quickly finish this one up first, then we can come to the SHM questions. Dhandresh, the question you have sent is SHM or it is some other chapter? So this will be density of water into 4 by 5 A cube into G. This will balance mg. Okay, okay. I'll see that also. Okay. So this is telling me that mg is equal to 4 by 3 into density of water into A cube into G. Now in this case, the free body diagram will look like there is a normal reaction that the other small particle is applying. So that is above ground, I mean above water. So it's not experiencing any buoyant force. And there is weight. And there is a new value of buoyant force. Okay. So the new value of buoyant force is density of water into A cube into G. So this will now give me an equation that capital Mg plus small mg is, so 4/5. It should be 4 by 5. So this is now so if you compare these two equations, you can see that capital Mg plus small mg is 5 by 4 times capital Mg. So you can see that small m will be capital M by 4. Okay, so Diti, I hope this question is also, you got the answer yourself. So we have okay, next question. I'm just putting up the question over here. We'll pick it up after you finish writing down this one. So we have, okay, very good. I will come to the other questions also. This is a question by Tantresh. The question sent by Tantresh. It is a question made by him. I would be even happier. So what is happening here is we have a combination of two liquids, which is in an open container. So this liquid has a density of 2 times rho, and this height is h. Whereas on top of that, we have another liquid, immiscible liquid. So assume it's like oil floating on water, something like that. And this has a density of rho. So now we have to find the efflux velocity. We have to find the speed of efflux. It's a small hole. Okay. So we have to adjust the derivation that we had done from Bernoulli's equation earlier for efflux velocity. We have to see how we can adjust that. So what I would advise you to try in this question is see the streamlines of this second liquid which is flowing out, which has density 2 rho. These streamlines are like this. So you can apply Bernoulli's equation between one point which is over here and another point which is just outside over here. One point is just below the interface. Okay, so apply Bernoulli's equation between these two and compare the sum of the three heads, and from that you should be able to get. Okay? And also, if this is coming down with some velocity v like this v will be very, very small compared to this, because the orifice or the opening is very small compared to the area of the tank. Okay, the orifice here is very small. So hope you understood the method I'm referring to, Tantresh. Okay, try it out by this. Okay. apply Bernoulli's equation between these 2 points, 1 and 2. Okay. The only adjustment you have to do is that point 1 is not an open surface now. So the pressure at that point will not be atmospheric pressure. You have to adjust the pressure properly. So when we apply Bernoulli's equation, we have like this: P1 plus half the density of that liquid is 2 rho. So half rho V square plus density into G into H is equal to P2 plus. Okay. Now we can see that P1 is equal to atmospheric pressure plus rho G into 2H, and P2 is equal to atmospheric pressure. Because 2 is a point just outside the orifice, so it's at under atmospheric pressure. As the point 1 is having that extra static hydrostatic pressure because of the liquid column above. Okay, so I will replace P1 with P0 plus 2 rho GH when I open that term. Okay. Okay. So cancelling of the common terms and all that, we can see that we'll get half of 2 rho into efflux velocity square minus V square is 2 plus 2, 4 rho GH. Okay. Now we will use the term that V is negligible compared to efflux velocity. So efflux velocity square minus V square is this. So this side of the equation becomes this is equal to so in this case the efflux speed or the efflux velocity will be this much. So just go through this carefully, Tantrish. We'll hope the solution is clear. Yes, Tantresh. The thing is, na, see, when we apply Bernoulli's equation to 2 points, na, they must lie in the same liquid. So we cannot apply Bernoulli's equation to one point which is in liquid 1 and the other point which is in liquid 2. So the point 1 has to be in the liquid which has the density 2 rho. Okay, just below the interface. Okay, that's important. So that's why, for example, we cannot apply Bernoulli's equation between a point over here and this point because it's in a different liquid. So that's the thing. That is the thing that is tricky in this question. Otherwise, it's a straightforward application. So I hope this is clear. Now, one more question from fluids. Okay, we will keep this as the final one from fluids because I want to discuss questions from SHM also mostly. So anyhow, coming back to this, there was this important question I wanted to discuss, which was part of the set that Diti had sent. So we have this kind of a situation here. Okay, so a tube kind of thing like this, open. Now these two arms are of same length, L from here to here. Even though in my diagram it doesn't look symmetrical, but it's. And this system is rotating about this with some angular speed omega. Okay. And we filled some liquid. So what you realize is because of the centrifugal force acting on the liquid, there's an outward sort of pressure gradient, a radially outward kind of pressure gradient. So what we'll observe is that the level of liquid in these two will be equal, but the level in the tube which is coinciding with the axis will be less. So in the question, so basically, let's say this is L1, this is L2. Okay. Now initially, when it was at rest, okay, is given that L1 is equal to L2 was equal to L. Okay. Now find the omega for which L2 becomes 0 and L1 becomes L. Okay, so what you'll understand is that because of the rotation about this axis, there is centrifugal force like this acting on the liquid. So this creates a pressure gradient. It creates a pressure gradient. Just like we had seen that, if you remember, in an accelerated tank, we had discussed, you have a horizontally accelerated tank like this, the level of the liquid becomes like this because the acceleration creates a pseudo force like this. So the pseudo force creates a horizontal pressure gradient. So like that over here, what happens is that the centrifugal force due to the rotation, okay, creates a radial pressure gradient. And that concept has to be used. So we will first derive the formula for the pressure gradient along the radial direction. And from that, we will solve the question. So ultimately, what we want to do is, let's say this point is A and this point is B or this point is C. Now you will see that because of this radial pressure gradient, pressure at B will be greater than pressure at A. Pressure at C will be greater than pressure at A due to this radial gradient, due to this radial pressure gradient. So that is the concept we have to correlate over here. Okay, and shall scroll up to the previous question for a moment and then we'll come to the solution of this one. Okay, so let's come to this one now. Right, Tej, I'll finish this and I'll come to the HC Verma questions after this. Okay. So here what we'll do is now, whenever there's rotation, your reference is always with respect to the axis of rotation. So with respect to the axis of rotation, at any point which is at some radial distance r, the pressure should actually be a function of r. Okay, because there is radial pressure gradient. So how to find that radial pressure gradient, whether you're on this side or on that side. Okay. So if you make a free body diagram of a small section of liquid here, which is of thickness dr and at a distance r. So on that section, you will see that there is force due to pressure like this. So pressure into area, slightly different pressure into area. Okay. And because it's rotating like this, there is centrifugal force acting on it. So that is dm omega square r. This is the centrifugal force. Okay. So P is the pressure at r equal to r, and P plus dP is the pressure at r equal to r plus. Okay, so now you can see that for that small section of liquid, force due to pressure from this side, force due to pressure from this side. Sorry. And then there is a centrifugal force, which is dm omega square r, because this is at a distance of r from the axis. So balancing the forces, you will see that dP into that area of cross section has to balance dm omega square r, and dm is the mass of that section, so it is rho a dr. So we get this relation that so we get that or this is the gradient. So as you go along the radial direction, the pressure increases by factor of this much. For a distance dr, the pressure increases by an amount of density into omega square into r. Okay. So now coming back to this diagram, if this point is A and this point is B and the distance between them is L, then from A to B, the change in pressure will become from 0 to L, because R is this distance. Okay. So pressure at B minus pressure at A is equal to rho omega square L square by 2. And similarly on the other side, you'll see, because this is also equidistant from this side, there is also L. Pressure at C is also this. So now if we want the condition of the problem to be satisfied, that the level of liquid in the middle one is 0 and the level of liquid on the outer two sides is L, then it will have to be something like this. So this is rotating with an omega such that this condition is satisfied. So now you compare this, you'll see that pressure at the point A is atmospheric pressure. Pressure at the point B is equal to pressure at the point C is equal to atmospheric pressure plus rho GL from the vertical gradient. But also from here, we have this condition. So PB minus PA or PC minus PA, which is rho omega square L square by 2 should be equal to rho GL. So from this, we get omega as square root of 2G by L. That should become the answer. Yes, we will do that question Diti, with the fluid mechanics and SHM. We'll do that as part of our SHM questions. There is one question in the examples as well as in the exercise also of HC Verma's questions. Acha, you have sent one doubt also. Yeah, I'll discuss that one also. Okay, now let's come to the HC Verma questions from SHM. So let me just pick up the question numbers first from here.
Just
Yeah, beta.
so just a minute, we show the latest question.
Yeah. I'm coming back. Okay, so Tej, we have to add question number 14, and Kshitij asked for question 19 and 26 and 25. Okay, so 14, 19, 25, 26. Okay, that is everything now. All right, so let's start with question number 14 from HC Verma's SHM exercise. Okay, just go through it, all of you will discuss. Okay, so let's go through question 14 from SHM. So I'll just put up the diagram. So you have this vertical spring mass system, okay, where the spring is attached from below to the block, and then there's also a smaller block placed on top of it. Okay. And so first of all, for the first part, that find the resultant force on the smaller block when it is displaced through a distance x above its equilibrium position. So first of all, we have to establish the equilibrium position. So in question 14, we have a situation like this, that smaller block lying on top of a larger block, like this. So it's doing vertical SHM. Now in this diagram, let me assume that this is in equilibrium. So it's in the equilibrium state. The acceleration is 0. So you can easily understand that the combined weight will be equal to the spring force. Okay, this will be compressed, my mistake, will be extended, so that the spring force will be like this. This is the tension. So now the question is saying that when, so as it is oscillating, at some time when you are above the equilibrium position through a distance x, at a position like this, what is the net force on this block? So right now, what will be the state of the spring? The spring will have this kind of a spring. This will be the state of the spring. So if here the tension was TE, now in this diagram the tension would have changed. Let's say T, and also this would have a downward acceleration. So we'll see that M plus mg minus T is equal to M plus ma. So M plus mg minus, now what is the compression of the spring in this diagram? It is the equilibrium state minus x. So if we compare this equation with this equation, we can see that acceleration is okay, or you can see that minus d2x by dt square is equal to omega square x, where omega square is k upon m plus. Now you look at the FBD of the small block for this situation here. So on that there is normal reaction acting and there is mg acting, and it has a downward acceleration. So the net force on it is mg minus normal reaction, that is equal to m. So that net force is equal to m into this acceleration. So that is the net force which is acting on the block at this moment. So that is the answer to the first part. I hope this is clear, Tantresh. So the answer to the first part, that at this point of time the net force on small m is how much? So the answer to that is this. This is the net force. Okay, now the second part of the same question. Find the normal force on the smaller block at this position. So just have to calculate the normal force at this position only. So mg minus n is equal to ma. So n is equal to this is the normal force. Now third part, what can be the maximum amplitude with which the two blocks may oscillate together? So this is where actually this term only helps us. Okay, we can see from here that for the blocks to remain in contact, okay, n should be greater than equal to 0. So now from this expression you can see that n is like this now. So n is minimum at x equal to a, that is the amplitude above equilibrium position. So n's minimum value will become m into g minus omega square a, and this should be greater than equal to 0. So this shows you that a should be less than equal to g by omega square, or a should be less than equal to because here this term is only your omega square. Okay, so hope this part is clear, Tantresh. This is the most tricky part of the question. So you can see the higher up you are above the equilibrium position, the lesser the normal reaction is. So at a certain stage, the normal reaction can become 0, but for that to happen, the amplitude should be this much at that point. Okay, very good. So that's this one. Next, we'll be moving on to 19th question. Okay, so make a note of this if required, and let's come to question 19 next after this.
So can you please take it, scroll it a bit up?
Sure. This question only, no? The first
Yeah.
part. Okay. Sorry.
Done.
Done.
Okay, so let's come to 19th question. Now 19th question is the type of question which is like, it's just a complication from mechanics which gets incorporated into this, because it is neither a series nor a parallel combination of springs. Rather, it is a combination such that we can show a sort of a constraint relation for small displacement. Okay, because that is what the question is also asking, to show that it is SHM condition for small displacement. Anyhow, first let me draw the diagram. So three walls like this, or three rigid surfaces. Let's say this is the top view and you're looking into a, like looking into a horizontal floor, which is smooth. So this object is attached to three springs supported by a horizontal smooth surface. So mg doesn't play any role because normal reaction balances it. These springs are connected symmetrically. They are also equal. So these two angles are 45 degrees each. Okay. And now what we have to show is that so this is the equilibrium state with all three springs in relaxed state. So we have to first of all show that if we take this as our, let's say, x-axis, then show that the oscillation will be SHM for small displacement along the x-axis. Okay, and find the time period. Is what we're doing. So that small displacement thing becomes important over here. Okay, because now you can see that from this situation, if we displace it along the x-axis, all three springs will come into action. Okay, and in general, the net force will be restorative, but may not be proportional to displacement from mean position. So, from here, if we displace the block like this, you can see that these two springs, okay, so if we displace this by x, let's say, so you can see that this particular spring will become extended by x, but these two springs will be compressed by a different amount in general. Okay. And this angle would also now be different. Theta would have become, okay, like this. So the net force on this block or on this object at this point of time it would have become like this, but we'll have to do some approximation for that x being a small displacement. Okay, but anyhow, let's understand first. So this spring will apply a force in this direction of kx prime. This spring will apply a force in this direction of kx prime, and this spring will pull it back with a force of kx. Okay, so these two angles being theta, you can see that the net force on the block will be the vector sum of kx prime and kx prime in terms of displacement from the mean position like this. So the net force will be now on this expression we have to use approximation that x is actually delta x. It's a small displacement. So once we do that approximation, we'll see that this will come out to be, with this approximation, we'll be able to show that the net force will be equal to some equivalent spring constant into x. Okay, so the thing is, from that we have to find what this equivalent spring constant is. But here the x will be replaced with delta x. So just take down the free body diagram and then we'll figure out how to do the approximation here. This is question number 19 from HCV. Okay, so now we'll understand how to do this small displacement approximation. So for small displacement, what we do is that from this initial state, let's say this point is moving with a velocity v along this direction, along this symmetry axis, which we have taken as a x-axis. So now forget about the springs for a moment. You can add the springs later. So if these 3 points are A, B, and C, you can see that at this moment, the point P's separation velocity with respect to the point A is equal to V. Okay. But these angles being 45 each, the point P's approach velocity towards B or the approach velocity towards C is V cos 45 or V by root. Okay. So therefore, in a small time, if it makes a small displacement like this, if it makes a displacement delta x like this, so in time delta t, delta x will be V delta t. But during that time, this length and this length, they will each change by a smaller amount because the component of velocity in that direction is lesser now. So this length would have changed to L minus delta x prime, let's say. And this would also symmetrically reduce to L minus delta x prime. So this delta x prime would be V by root 2 times delta t. Okay, because this delta x is the separation velocity of P from A into time. Whereas this delta x prime is the approach velocity of P towards B or C into delta t. So that's why it is. Okay. So from this equation and this equation, you can see that delta x prime is delta x by root for small delta x. Okay. And then that this angle is also more or less 45 degrees. So now coming back to that free body diagram, at the point where it is displaced from the origin by a small amount delta x, the spring forces acting on it will become like this. K delta x prime, K delta x prime, K delta x at theta equal to 45 degrees. So the net force, which will give it an acceleration in this direction, will be K delta x plus 2K delta x prime cos theta. Now substitute this relation and substitute this value. Okay, so the net force will become okay. So from this you can see your equivalent spring constant. In this particular case is becoming 2K. So time period, but this is all for small displacement. If delta x is comparatively large so that we cannot apply this approximation, then while it will still oscillate, but it will not be a harmonic oscillation. So the time period cannot be calculated by this kind of formula. So that goes beyond the scope of our discussion over here, because we have to limit ourselves to harmonic oscillation. So hope this question is clear. Okay, so Kshitij, I'm hoping that this question is clear to you now. The trick of that small displacement, how we have to use that thing. So now next, let's come to 25th question. So question 25 is something in which we will use Acha. Okay, finish writing this down. Back to that. Okay, so let's move on to the 25th question. So 25th question is again, we have to use the concept of center of mass additionally from mechanics, in addition to the simple harmonic motion concepts.
Excuse me, sir.
Yes, yes, beta.
Sir, we have another lecture at 6:15. Can we please end it here?
Okay, then we'll pick up this. Actually, you have another lecture today, no? All right, so we'll pick up this 25th question in the next session that we have. Okay.
Sir, can you please scroll it up a bit?
Okay.
The last
So
question. I just missed
yeah,
noting the last one.
yeah. So next week we'll again put aside maybe 45 minutes or an hour for the doubts discussion in the first lecture that we have of SHM, and then continue with the next part. And we'll complete all these doubts in that. Okay. So that's it for today, people. Wish you all the best. Have a nice day.
Bye. Thank you.